Hi everyone, I'm Richard. I'm a PhD student at the University of Münster, and today I'd like to introduce you to Mdh-Dsl. So as a quick overview, Mdh-Dsl expresses data parallel computations in a reduction-aware manner. It allows user-defined reduction operators, and it is grounded in the MDH formalism, so it has a strong theoretical background. And you can find out more about MDH on our website that's accessible via the QR code on the top left. So let me first start with some examples that showcase the limitations in terms of reduction handling of existing DSLs. And for that, I'm going to show you the implementation of the well-known standard example matrix vector multiplication in several DSLs with reduction-relevant parts highlighted in red. So first up is Halide. The program is an intuitive C++ program where we have inputs as function parameters, define an output buffer, a reduction axis, and finally the computation itself in a format that resembles kind of an einsum notation. And while Halide explicitly expresses reduction operators in its DSL, like the plus, for example, we see here, it is limited to a fixed set of built-in ones. And furthermore, due to the einsum-based notation, Halide also has limited support for nested reductions that are used in computations from deep learning, for example, as we will see in a moment. Then we have TVM. It uses Python as the host language. And again, the program is pretty intuitive. We get the input sizes as parameters, define input and output buffers, a reduction axis, and finally the computation. And similar to Halide, TVM also has limited support for nested reductions. And while it does offer an interface for custom reduction operators, it is quite limited. Lift is a functional approach based on a solid formal foundation. However, it also struggles with nested reductions because it operates on one-dimensional lists as its fundamental data structure, for example. And so while Halide struggled with nested reductions due to its einsum notation, Lift has difficulties, especially because of its strictly functional style. And finally, we have Lineage. That's a polyhedral-inspired representation. And for matrix vector multiplication, we basically specify the accesses to the input and output data and a small code snippet that computes the multiply add for one element of the matrix and the vector. As you can see, reduction operators are not first-class citizens in its language design. We simply specify that the second dimension is a reduction dimension, and the specific operator that is used is incorporated into the computation itself. And this severely complicates optimizing and parallelizing reduction-based computations in Lineage. With Mdh-Dsl, we address the issues that we have analyzed and identified in existing approaches. We base Mdh-Dsl on Python to maximize accessibility for application developers, and we see three major advantages it has over existing DSLs. So first, in contrast to Lineage, reductions are first-class citizens in our language design. So for example, you can see that in the first iteration space dimension, we use CC to concatenate intermediate results, and in the second one, we use pointwise add to sum them. Second, in contrast to Halide, reductions may be arbitrary Python functions that satisfy some obvious type properties, and we also provide some pre-implemented ones like CC and pointwise add, for example, because they are so heavily used in real-world applications. And third, in contrast to all aforementioned approaches, nested reductions can be explicitly expressed in Mdh-Dsl. And again, we can see this in the MATVEC example where we use CC for the first and pointwise add for the second dimension. And this comparison is also summarized in the table below the figure. We have evaluated Mdh-Dsl for two case studies. The first one is a real-world case study from deep learning, and we can see that explicit support for nested reductions achieves notably better performance than handling nested reductions in a flat manner. And the second one is a real-world case study from data mining, and again, we can see that explicit support for custom reduction operators also achieves notable speedups. Below that are further highlights of our experimental evaluation, and they show that we are often even able to outperform hand-tuned vendor libraries, for example, NVIDIA QDNN by up to 2.4x or Intel 1DNN by up to 3.9x.